In this screencast, we're going to work through a flash distillation problem for a binary system, but focusing really on the energy balance. So we have our flash drum here, and we know out of this drum we're going to have a vapor stream, I'm going to label V, and we're going to have a liquid stream, I'll label L. This vapor stream is going to have some mole fraction of water and some mole fraction of ethylene glycol. This liquid stream will have some mole fraction of water and some mole fraction of the ethylene glycol. We have a feed coming into the drum that goes through a valve that causes it to flash, and we may have some kind of heater, it looks like, that is going to be before the valve to heat or take away heat from the incoming line. So this feed I'm going to label F, and we're going to use Z as our mole fraction of water and mole fraction of ethylene glycol. And this has some temperature F, this has some temperature for the drum that we are looking for. We know that this feed here is 40% water. We also know that the feed is at 300 kilopascals and 150 degrees. And we know the pressure of the drum is 30.4 kilopascals. And at 33% of the feed is vaporized. So let's write out our approach to solving this problem. So the first thing is get our vapor-liquid equilibrium information for the species and plot an XY as well as a TXY diagram. We're going to utilize what we know. In this case, we know our fraction of the feed that's vaporized. This is going to help get our mole fraction in liquid and vapor streams, which will give us T of the drum. Once we have T of the drum, we can solve for the enthalpy associated with the liquid stream as well as the enthalpy associated with the vapor stream, and this will allow us to solve for the enthalpy of the feed. And since we know the enthalpy of the feed, this will help us get Q. And as you can see, if we have Q, then we can reevaluate the enthalpy of the feed to figure out what the temperature of the feed would be. So I've plotted the vapor-liquid equilibrium data on an XY diagram for our system at the 30.4 kilopascals. And the first thing I would do with this graph is add our x equals y line. And we've talked about that in previous screencasts for the derivation of flash calculations. And what's important also to take away from this is to write the operating line based on the material balances for our flash tank. And so this can be the mole fraction in the vapor phase for our species is the following equation, where we have V over F as the fraction that's vaporized. This is multiplied by the mole fraction in the liquid phase. This is plus mole fraction in our feed over this fraction. So since we're given V over F in the problem statement as 33%, we get the following equation for our operating line for this system. So again, this is for water, and I get this value because we know that Z of the water is 0.4. So to draw this on our XY diagram, we go to the composition of our feed, which is at 0.4 for water, and then we draw this line. So this says that the solution to our system is where these two intersect. So now we could determine the composition of water in the liquid stream by drawing a line down, and we could determine the composition of water in the vapor stream by drawing a horizontal line. This says that X of water is equal to about 0.17, and our mole fraction of water leaving in the vapor stream is equal to about 0.88. Now that we have the mole fractions at equilibrium, we go to a TXY diagram, and we want to determine what temperature that these two compositions are at equilibrium. So we'll draw a line up from one of the 2 points. I'll choose about 0.17. We come to where it intersects, and then we could draw a horizontal line across from where it intersects on this graph. And if that satisfies our graphical interpretation, then you could see that this horizontal line is at 115 degrees. Therefore, the temperature of the drum must be at 115 degrees Celsius. So we've answered the first part of our question, the temperature of the drum. So when we look at our flash tank, we could do an overall energy balance. And that says that the enthalpy of our feed times our feed flow rate plus any energy we add to it must be equal to the enthalpy of our vapor stream times our vapor flow rate plus the enthalpy of our liquid stream times our liquid flow rate. And of course, this is enthalpy per amount. And so now we need to determine our enthalpy of our feed and our vapor and liquid streams. Because we have the temperature for these streams, we could determine the enthalpy. So let's quickly work through that. So for the liquid stream and the feed stream, since we're feeding a liquid, we could treat these the same. And this is going to be a weighted average of our two species contributions. And so if we do it this way, we may get a more accurate answer. So our reference, I'm going to use 25 degrees Celsius liquid states for both of these. And we're going to make a pretty big assumption here, and that's going to be that our delta P is not going to contribute much enthalpy and is going to be negligible. So for the liquid enthalpy, I get 27.097 kilojoules per mole. For the enthalpy of our feed, I get 33.598 kilojoules per mole. And again, these are both liquid states. The third one that we need is the vapor. And the only difference here is we have to take into consideration the enthalpy associated with the phase change. So we're going to use the enthalpy of vaporization, and that's something you would need to look up as well. So here we have the mole fraction of water in the vapor stream times the heat of vaporization of water plus the same integral we had before, and we would repeat this for the other component. And when we do this, I get an enthalpy associated with the vapor stream of 52.328 kilojoules per mole. So now we can plug these values into our energy balance and use the following. And this allows us to solve for Q. And when I do this, I get roughly 191,000 kilojoules per hour of heat that needs to be added to the feed stream to satisfy our energy balance. And that's sometimes typical to preheat the incoming stream to a flash tank. If this process were adiabatic, the last part of our problem, then Q is equal to 0. The only difference here now is that by setting Q equal to 0, we don't know the enthalpy of our feed. And this drops out of the equation. So we could solve for HF, which gives us 35.507 kilojoules per mole. So that's our specific enthalpy for our feed. We then go back to how we calculate the enthalpy of the feed, and we know certain values. For instance, we know that this is 0.4 and the other component therefore is 0.6. Again, we can enter these heat capacity coefficients in. From the mathematical perspective, solve for T of the feed that satisfies this equation. And so the best way I do this is, since I set everything up in Excel anyways, I could goal seek what this equation is given me to equal 35.507 and determine what that final temperature must be. And when I goal seek this, I get a feed temperature of 155 degrees Celsius. So not much more to heat it, but you could see and guess from part 2 of this that since we had to add heat, if our temperature of our feed just had a higher temperature to start with, then we would probably not need a heater.